Alright, for this presentation I will start with the motivation of this work, the experimental procedure, the results, discussions, and finally the conclusion of this work. Nanoparticles are the fundamental building blocks of nanotechnology. For some technologies, for instance intermediate band solar cells, they are the raw material for manufacturing this kind of nanostructured devices. However, manipulation of these nanoparticles is difficult and critical. A method to carry and deposit these nanoparticles is in nanoelectrospray laser deposition, where an aqueous suspension of nanoparticles, that is an aqueous ink, is used as a precursor to produce micro and nano droplets via electrospray, and a laser beam is used to evaporate the liquid and simultaneously sinter the nanoparticles. In this particular method, droplets interact with a laser beam as they are ejected from a nozzle and subsequently impinge on a laser-heated substrate. We can see then that this kind of work has applications on spray cooling of hot materials, spray coating, or even combustion engines. Therefore, the understanding of thermal response of liquid droplets is important. The dynamics and thermal response of droplet impact on hot surfaces has been extensively investigated in the past. In most of the studies performed to investigate the outcomes in a droplet impingement problem, homogeneous liquids have been used as well as uniform heating of the substrate via thermal resistance. But here we use laser radiation to investigate the thermal response of microdroplets. Tiny microdroplets with diameters around 70 microns that carry semiconductor and metal nanoparticles for inkjet printing applications. Understanding of the dynamics of impact of microdroplets is important for the deposition and sintering of nanoparticles for fabrication of nanostructured devices like the one that I am showing on the right, an intermediate band solar cell. If we look at this slide, it shows experimental setup used to perform this study. First, droplets are formed by forcing an aqueous suspension of nanoparticles from a syringe pump at a flow rate of 10 microliters per minute through a stainless steel flat-tipped hypodermic needle that is a capillary tube of inner and outer diameters of 0.5 and 0.8 millimeters respectively. The separation of the needle tip from the substrate is 8 millimeters. Additionally, an electrostatic field is created by applying 3000 volts between the needle and the substrate, which work as electrodes. Subsequently, microdroplets ranging from 70 to 80 microns are generated using this electrospray. Eventually, these droplets interact with the laser. Here, we have the optical setup. First, an ND-YAG laser of 1064 nanometers is used to create a Gaussian laser beam. This Gaussian beam is converted into a laser ring by using an oxycon lens and a biconvex lens. Finally, this annular beam is converted by parabolic mirror into a hollow conical beam. The laser beam interacts with a droplet on a stationary point while the substrate is moved at a specific speed. In this figure, we can see how the hollow conical beam interferes with itself, creating a Bessel beam. This Bessel beam interacts with a droplet, and therefore the intensity is enhanced below the microdroplet. An ideal Bessel beam can be represented by the expression shown in this slide, E equal E naught times Jn, which is the nth order Bessel function of the first kind. Kr here is a radial wave vector and Kz is a longitudinal wave vector. On the other hand, the time average intensity of the beam can be described by the following expression, J naught of Kr and R squared. For measuring the thermal response of the Bessel beam heated microdroplets, different fluids were tested, and those are the ones that are shown in this table. We can see that we have first a surfactant solution. That means that it has zero concentration of any nanoparticle. And then a solution of germanium with 5% concentration in weight and 10 weight percent as well. And silicon, 5 weight percent. And finally silver with a concentration of 20% in weight. This table shows the different physical properties of interest. In this case, we care about the density, viscosity, surface tension, of all these liquids, as well as the optical properties such as reflectance at a wavelength of 1064 nanometers, the absorption coefficient at this same wavelength. After using high-speed imaging and image processing, results suggest that at the impact of nanosuspension microdroplet onto the surface that is heated above the boiling point of the liquid, the microdroplet either instantly boils after collision on the surface or, without any contact with the surface, develops a latent frost vapor layer beneath the liquid surface and bounces back. On the other hand, if the localized temperature of the droplet impingement spot is below the boiling point, the nanosuspension microdroplet spreads radially, forming a film that gently evaporates. In this animation, you are looking at three different cases. In all of them, the flow rate is 10 microliters per minute, and the applied voltage is between 3,300 to 3,800 volts. The distance between electrodes is 8 millimeters, but what changes here are the liquids that have different physical properties, as well as the laser power that is being used for sintering the nanoparticles or for evaporating the liquid of the microdroplet. First, we see that in the animation on the left, the droplet laser interaction at this laser power, that is 8 watts, and the substrate temperature allows the droplet to assume the shape of a flattened disk. We call that sessile droplet. These droplets are patterned as a linear array by moving the substrate, and that's what you are seeing there. In the animation of the center, we can see the interaction of the characteristic cross-section intensity of the Bessel beam and the curved liquid surfaces or ripples. Due to active boiling of the droplet, the fringes that are visible in this animation are visible only during the time that the pulsed laser is on. The brighter spots inside the droplet suggest that the laser beam was refocused by the multiple ripples of small radii of curvature at the surface of the liquid. And finally, if we look at the animation on the right, we see the bouncing of a droplet on the surface. The surface is a silicon substrate that is being heated in such a way that the temperature of the surface is 137 degrees Celsius, and this happens for a laser power of 22 watts. We can see that above certain critical laser power, the substrate surface is excessively heated by the laser, and the interfacial tension at the substrate droplet interface changes significantly, resulting in a restricted spreading of the droplet on the substrate. The combined effect of the stored energy and the surface tension pulls back the spreading droplet to its original shape. The upward bouncing of the droplet is due to localized rapid evaporation of the liquid at this point, and this results because of the latent frost effect. Here we see that rapid evaporization causes accumulation of vapor underneath the deformed droplet and builds up pressure that ultimately propels the droplet upward, as we can see in the animation on the right. Now, by taking those videos and extracting images, we can see the sequence of each phenomenon. First, we see on A how the stretching of the electrified meniscus and formation of monodispersed microdroplets takes place. The images on C show the droplet laser interaction at a lower temperature. This allows the droplet to assume the shape of a flattened disk, that is a sessile droplet, while figure D shows the droplet laser interaction when the laser power is increased. And finally, E shows the droplet rebound when the laser power has been increased further. This figure shows a regime plot of the different outcomes observed when the liquids were tested. That is, we can see how the surfactant solution, germanium 5 weight percent, germanium 10 weight percent, silicon 5 weight percent, and silver 20 weight percent behave as a function of the absorbed power of the laser. The formula for calculating this absorbed power is shown on the right, and we can see how it can be obtained by integrating from 0 to R naught, which is the radius of the droplet, P naught, that is a characteristic power that depends on the laser input power, times the intensity of the beam, times 1 minus the reflectance of the droplet, times 1 minus e to the minus mu hr. Here mu is the absorption coefficient, so do not confuse it with viscosity. And HR is the depth of a liquid interface as a function of the radius. Although the Young's equation is a good approximation of the contact angle at the macro scale, and we could potentially use this for getting HR, it doesn't really predict well experimental results in micro and nanoscales. That's something we noted. Thus, we got HR experimentally, and we approximated basically the interface as a spherical cap, giving an expression for HR. From these results, we can see that the transition to contact boiling regime occurs at approximately 100 Celsius. This occurs obviously because all the liquids tested were prepared by suspending nanoparticles in deionized water. At this temperature, the water starts to boil, and the presence of nanoparticles promotes heterogeneous boiling. Heat is then transferred by conduction from the solid substrate to the liquid microdroplet, while the entire droplet is additionally heated by the laser. The nanoparticles suspended in the liquid act as nuclei, and vapor bubbles are generated at the nanoparticle surfaces. Moreover, the substrate temperature is increased as the laser power is increased, and this causes a more active heterogeneous nucleation that generates a pressure increase within the boiling droplet that finally produces bursting of vapor bubbles and ejection of liquid ligaments in the air, as it can be seen in the inset picture. On the other hand, contact boiling of the microdroplets is seen between temperatures of approximately 100 Celsius to 138 degrees Celsius. After the surface temperature of the substrate exceeds a value of approximately 138 Celsius, then the post-collision dynamics of the microdroplets is characterized for a restricted spreading of the liquid and a rapid recoil that doesn't allow the dissipation of its original kinetic energy. Subsequently, then the microdroplet bounces back from the substrate, and that's what we can see on the inset figure next to microdroplet rebound. So the bounced droplet recovers its spherical shape due to surface tension. It reaches certain height until the kinetic and potential energy are balanced, and then it falls down again onto the substrate. And this happens many times. It is not restricted just to one time. Another observation is that the characteristic vapor layer in the latent frost phenomenon insulates a droplet from the hot solid surface. Thus, the droplet doesn't experience nucleate boiling and bounces back because the vapor over pressure beneath the bottom surface overcomes the droplet's dynamic pressure. Now, this phenomenon is detrimental if the objective is to deposit nanoparticles on the substrate, since this inhibits the evaporation of the continuous liquid and subsequent sintering of nanoparticle on the substrates. Thus, the ability of delineating this, that is, the transition between contact boiling and droplet rebound, is fundamental for the positioning and laser sintering of nanoparticles. Well, and finally, we can talk about the conclusions. First, the thermal response of Bessel beam heated microdroplets that carry semiconductor and metallic nanoparticles was investigated. 4 different outcomes were identified in a phase diagram showing 4 regimes: heating of sessile droplet, contact boiling of microdroplet, microdroplet rebound, and laser spraying of microdroplet. The transition between the first regime and the contact boiling is found to be at the surface temperature of approximately 100 Celsius. On the other hand, the transition between contact boiling and droplet rebound, and perhaps the most important one, occurs at approximately 138 Celsius. Also, microdroplets of 20 weight% concentration of silver in DI water experienced a different phenomenon, that is a laser spraying regime. This transition, in fact, blemishes the dependence of the latent frost temperature on the solid surface for liquids with low reflectance and high absorption coefficient. This is the case of the silver nanosuspension. And finally, the laser microdroplet interaction influenced the quality of nanoparticle deposition on the substrate.